Hey everybody, I'm not sitting in my chair today because I'm in my basement. I want to talk to you about the solution process, which also includes the precipitation process. You see those inlet valves, hoses to my washing machine? Look at all that precipitation. And you can only blame it on one thing: calcium carbonate. And why does my water heater make a funny popping noise? Buildup of calcium carbonate. And why does this shower head keep getting plugged up? One thing: calcium carbonate. And why have I had to buy 3 coffee makers in the last 2 years? Simple reason: calcium carbonate buildup. What up everybody, what up? Mike here. Today we're going to talk about the solution process. And sorry, I got all negative on calcium carbonate there, but calcium carbonate is quite the menace. So what I'm going to do here is do a little demonstration. This is what we call in science a bowl of water. And this is iodized salt. And so what we're going to do is we're just going to take some of that and we're going to dump it using a process we call in science dumping. And I'm going to let it sit there, and I'm going to stir it with, we don't have appropriate lab equipment here, but it's only salt water. And you will notice that the solid still remains there. And that's because, and it will, because I can tell what I've done. Well, let me make sure I'm not lying. Maybe if we came back an hour later, that it would all be dissolved, but certainly not now. And you see what's going on there is I have gone to and exceeded the saturation point, or what we call the solubility limit of that salt in water. And no matter how much work I do to that solution, there's a point where just no more will dissolve. So let's take and let's do a thought experiment here with actual numbers. And by the way, whenever you're doing a thought experiment, you should always wear your thought safety glasses. So this is going to be a beaker of water. And I'm going to use nice round numbers. And we're going to do exactly what in our thought experiment. We're going to make this 100 milliliters of water. And we're going to say, what if I were to take some 50 grams of NaCl? 50 grams. And I go ahead and put that in there. And you might say, well, I don't know. Is all of it going to dissolve, or is not all of it going to dissolve? Well, I'll tell you right now, if we had this number right here, which is 35.7 grams of NaCl per 100 milliliters, we call this, and by the way, at 25 degrees C. So we'd have to go look that up and find out, okay, so that's what we call the solubility limit. We should write that down. That's the solubility. Sometimes they just call it the solubility, but this is it's a limit. That tells us that what's going to happen here is that 35.7 grams is going to dissolve. 35.7 grams NaCl aqueous. Fair enough? What's going to happen to the other 14.3 grams? Well, it's not going to dissolve, and it'll go to the bottom. How do we know it's going to go to the bottom? Well, remember all those unit cell problems we did? Solids are generally more dense than water, and that is going to go to the bottom, and we have terms for this. This is called a precipitate. And This is called a saturated solution. Some of my people will say, hey, that's super saturated. Well, you're overusing the term super. You're super excited, I get it, but you're using the wrong term. That's just saturated. And by the way, if we put 25 grams of NaCl, it would all dissolve, and that would be unsaturated. So we've gone past the saturation point. Super saturated is if you start doing tricky things where you can get that solution to increase its solubility limit by changing the temperature and then cooling it slowly, and you could actually trick the solution to hold more than the solubility limit, because sometimes things need to precipitate on surfaces. But if we're just talking about dumping the max number of, over the maximum number of grams of NaCl in that sample of water that can dissolve, that's just a saturated solution. Now, folks, I'm going to go a little bit ahead of where most textbooks are, and we're going to talk about the fact that this is a state of equilibrium. And out here, for the first time, we're going to bring the double arrows. It doesn't even matter what's on either side. I could put aqueous on the right or left, and the reason it don't matter is because we're at a stalemate between those two phases. What's going on is that there's no net precipitation or no net dissolving. That stuff is just going to sit there. And there's different kinds of equilibrium. There's what we call static equilibrium, which is, this is what this situation is. This is a case of static equilibrium, meaning you dump the stuff in there, there's only so many ion dipole forces that can allow so much water molecules to interact with so many ions, and then it stops dissolving when all those interactions are taken up. But later on we'll talk about dynamic equilibrium, like the stock market is a dynamic equilibrium. A price of a commodity or something, it depends on supply and demand, and the price doesn't change when there's equal numbers of buyers and sellers. That's kind of more like, that's more like dynamic. But a solution, dumping something in water until it gets to its saturation limit, that is a case of static equilibrium. Now, do you notice that when I quoted the solubility limit, that was at a certain temperature? Because if you change the temperature, the solubility changes. And so you say, hey, everything must increase when you heat it up, right? Everything gets more soluble. Nope, that's not how it works. Because what's going to happen is equilibrium situations or systems can shift towards the left, right, towards aqueous, solid, and the way you can shift those is with temperature or pressure. And we're going to talk about those today, but first we need to define something that is very important called Le Chatelier's principle. But let's take into that little break this idea. Where's heat? You folks are experts in thermodynamics. Is heat on the right? Or is heat on the left? Where is it? That's going to determine what gets more soluble as you heat it or what gets less soluble as you heat it. Now, spoiler alert, sodium chloride gets more soluble as you heat it, slightly. But not everything that's ionic does that. How about calcium carbonate? Precipitating in the coffee maker, in my washing machine, in the shower heads. The warmer that is, the less soluble it gets, and that's a real problem if you ever go look at your supply hoses to your washing machine, or if you've ever had a coffee maker die of hardening of the arteries like mine has. And I live in Beaver Creek, Ohio, where the water is so hard you can chew it. So there's tons of calcium carbonate. So it's two different scenarios. Let's talk about what makes something more or less soluble next. Warning, whoop, whoop, warning, whoop, whoop, important concept alert. This is Le Chatelier's principle. And it says that if a stress is applied to an equilibrium, the equilibrium will shift to counteract the stress. Okay, so let's start. We just got done talking about heat. Let's talk about temperature being a source of heat, of course, or a manifestation of heat. And so we're going to go back to our NaCl example. And I'm going to go ahead and tell you that NaCl, when it dissolves, has heat on the left, and I'll go ahead and put heat here on the left. And then we have a name for that. That's called enthalpy of solution, heat. And I'm going by the top of my head here, but I would say we'll give it delta H solution. I want to say it's 6 kilojoules per mole positive. Positive, of course, back to Gen Chem 1, that means that the heat is kind of like a reactant. So, okay, some things have a positive delta H of solution, some things have a negative. NaCl has a positive. So, if we were to add heat to the situation, what would that do? That would be like adding something that's on the left. And this is kind of like a state of balance. That's why they call it equilibrium. And think of this as, before I added heat, this would come to a state of balance, 35.7 grams per 100 milliliters of water. And it would just sit there forever. Now we're going to go heat it up. Now we're adding heat. What's going to happen then? That's going to be kind of like overloading the left side of the equilibrium. And the only way it can counteract that stress is to get rid of the heat, right? And so what will happen is this process will increase greater. I'll make the arrow more bold. And so the rate of it dissolving will increase, and that will dissipate the heat, and that's how it counteracts the stress. And so as you heat this, it will become more soluble because of the positive delta H of solution. What if you do the opposite? If you were to remove it, removing heat would then make this side of the equation too light, if you will. And so the way that the equilibrium could counteract that stress is if the other process were to increase, which is the process of precipitation, which in turn will generate more heat and replace the heat that was lost. So basically we have two results here for NaCl. If we were to increase the temperature, then it would become more soluble. So that solubility limit I quoted before, 35.7 grams per 100 milliliters, well, you heat it up, it would increase. That's why they always quote a solubility with a temperature. Usually they do everything at 25 degrees. If I were to decrease the temperature, that would be solubility decrease. Is everything like that? No. Calcium carbonate would be the opposite. Calcium carbonate would have a negative delta H of solution, and if you heat it, it would become less soluble, and that's a real problem. That's why you find scale in your water heater. It's why your coffee maker has deposits all over. It's why if you look in a spaghetti pot, if you have a little bit of hardness in your water, there's residue. Let's use something more exciting for you folks that have environmental aspirations. Let's say we were going to take oxygen. Ooh, I could tell a story. O2 gas. O2 aqueous. Now I'll explain why, but gases also almost always have an exothermic delta H of solution. Delta H solution equals negative, all right? Oh, here comes a story. Once upon a time, Mike got a goldfish from the carnival. I won in a game. I named him Larry. And then what happened to Larry is I was thinking, I'm going to clean his bowl, because I had to clean his bowl. He was making a mess of it. So I cleaned out Larry's bowl, and I said, I was just a dumb kid. I said, what I'm going to do is I'm going to give Larry a nice warm water bath, and you know, he'll have a nice bath like when I take a bath. Well, you know what I did to Larry? I ended up killing him. That's the end of the story, because and I thought, oh boy, he looks relaxed in that warm bath. No, he wasn't relaxed, folks. Well, he was permanently relaxed, because what happens is the solubility of oxygen in water is actually something that becomes lessened as you heat it. So you've heard environmentalists, you can do a lot of destruction to aquatic life with just dumping hot water and stuff. If you're outside a factory that just dumps hot water as refuse, you can kill a lot of the plant and other kind of life, because what will happen is this will make heat will be now on the right, and if I add heat, increase temperature, then what will happen is the solubility will decrease. Aqueous becomes gas, and so this would be, you know, solubility decrease. And as a matter of fact, I'm going to make a sweeping statement. All gases are like that. All gases get less soluble as you heat them. So for example, you might notice that you know, you can do this trick. If your water tastes like chlorine and you don't like the taste of it, chlorine's a gas. You can just basically heat it up, boil it if you wanted to, and then cool it down, put it in your fridge. It'll taste a lot less like chlorine because you'll have gotten rid of all the chlorine. So something like that. If you were to heat a carbonated beverage, it's been in your trunk for hours, and then hey, I'm going to pop this root beer because I'm thirsty. You'll notice carbonation, CO2, is something that really does not dissolve well when it's warm. So, but if you decrease the temperature, then you will notice that, well, in this case, water would become more oxygenated. Your carbonated beverage actually holds onto its carbonation more, then decreased temperature, solubility increase. So folks, do I expect you to know every single dang delta H solution in the world? No. But that tells you the direction. If you were given that data, you would be able to tell, oh, okay, this is a delta H solution of positive. Therefore, I know when I heat it, you have to put this scenario together in your mind, and you say, oh, I heat it now, I know it's going to shift it to the side of it being more soluble. Whereas if the delta H solution was negative for anything, calcium carbonate, something that's ionic like calcium carbonate, or all gases, then you know that heating it up makes it less soluble. And now you understand, in terms of Le Chatelier's principle, why certain things become more or less soluble when it comes to temperature. That's the whole thing. Not everything gets more soluble when you heat it. Some things get more soluble when you cool it. It depends on what side delta H solution is, or what depends on what side heat is. So let's talk more, except now we'll talk about pressure. All right, folks, we're going to talk about something exciting. We'll talk about CO2. That's exciting. We like carbonated beverages in our society. And so what we're going to do is we're going to talk about, here's a container of water, and it's in a sealed container. And now what I'm going to do is I'm going to inject some molecules above it of CO2. It's a gas. So what's it doing? It's, you know all about gases. It's moving around randomly. I'm going to put some more molecules in there, moving around randomly. Some of them aren't banging into the water molecules, but some of them are. In the case of CO2, it has London forces. It can be polarized. It would dissolve in the water molecules every once in a while. Here's a molecule. It hit that, and now it's stuck. Now it's stuck and it's dissolved in there. And now it's just common sense, folks. There's a law called Henry's Law. It just says this: solubility of a gas is equal to some constant times the pressure. So that's solubility. This is pressure. Let's say this little cartoon I made, I'm going to double the number of gas molecules above it. So I'm going to make these colored in like they're that. So there's 4 molecules. Now I double that. and I make that into 8. Sure, some of them are bouncing around aimlessly and not doing anything like dissolving, but once in a while one of them's going to hit, and now I just doubled the solubility. So you know this is X and that's Y. If I make this 2Y, it would be 2X. It's just probability, folks. And so what's happening here is that you want to look at this like Le Chatelier's principle. If I increase the pressure of gas above the solution, I'm going to shift that equilibrium to the right. Now, let's talk about fun stuff. We'll make it wholesome and make it root beer. Root beer? Yeah, we'll talk about root beer. If you take a plastic bottle of any sort of carbonated beverage that'd be your root beer, it's usually pressurized to 5 atmospheres of pure CO2. If you were to then pop the top on it, here we go. Now this is a bottle. Looks like an awful awkward looking bottle, I know, but it's, now I'm gonna let all these out. I can't erase them, but out come molecules like when you release that. Now these are gone. What's gonna happen? The solubility of the CO2 is going to decrease because the pressure over that has increased. So back, if I were to recreate this, aqueous over here on the right, CO2 gas on the left. If I decrease that pressure, that's going to shift this to the left, and it's going to become less soluble as it shifts away from CO2 aqueous, and it's going to precipitate. Except when gases precipitate, they make nice, pretty, pleasing bubbles. And back in the past, someone figured out, hey, if we ferment things in the container, like champagne, I think I said that in French. If you take champagne, you know, the pressure gets in so big that they actually have to pop the cork on and let some pressure out. But it'll be carbonated by fermenting in there. And that's how beer would be too, except I don't really think, when I made my own beer once and I fermented it in the bottle, and you put the top on, the cap on, and then some of them explode. But you see, what'll happen is that'll increase the pressure. So pressure is kind of easy to understand, that if the greater the pressure is, the more probability of a gas molecule is going to whack into a water molecule and stick. And so that's easy to remember. The heat thing, a little bit harder, because you have to put it together and know which side of heat is it on, and that's that. Let's try to wrap this up and put a nice tidy bow on this next. All right, so now what I'm going to do for this little graph, or chart I should call it, I'm going to try to wrap up every single scenario of what could happen. If I write an up arrow, that means increase solubility. And if I write a down arrow, it means decrease solubility. So, okay. I've got solids and liquids, something with a delta H solution that is negative. I got to put that scenario together. Heat is on the right. I increase temperature. I add heat. That means the solubility is going to go down as it shifts to the left. Fair enough? So something that is a solute, that is solid or liquid, if it's got a negative delta H solution like Prestone driveway heat and I heat it up, you can put it in water to determine which way the delta H is, positive, negative, but then that determines what happens if you were to go and heat it or cool it. And it's the same thing. If I cool it, heat's on the right, and therefore it's going to be removing heat. The equilibrium will shift to replace that. So that takes into account our example with, we used oxygen. But that's a gas, but it's the same situation down here. Increased temp. Gases are all delta H negative, so increased temp. And then if we decrease the temperature, same thing. So, you know, gases are all delta H solution negative. They just are, trust me. The opposite, like salt, would be true. If heat was on the left, adding heat overloads the left, it'd have to shift to the right. That would make that dissolve more. Anything with a delta H solution negative. And then of course, if you understand the one way, you understand the other. Decreasing temperatures, taking away heat that's on the left, that would make that decrease. Now, notice I didn't say anything about pressure when it comes to dissolving salt, because gases are compressible and solids and liquids aren't. So if you had something like salt and water and you put a ton of pressure on it, well, everything's underwater. It's not pressurizing it. It's not compressing anything. Everything, liquids and solids are virtually completely compressible. So we're not even going to discuss pressure up here. That's only for gases. And as we talked about, increasing pressure makes the solubility go up proportionately. Increase the pressure 10 times the solubility. And same back and forth. That's about everything we can do to a solution to make it dissolve better or worse. And that's only really factoring in two variables, which is heat and pressure. And so if you're a scuba diver, you know this business. If you come up too fast, you can have all sorts of blood gases come out way too quickly, and that's dangerous. You could have the bends. So they put you in a hyperbaric pressure chamber to kind of undo that. And so that's a little other tidbit of information too. So that's about everything you need to know about the process of making a solution and how we can affect something's solubility. Next time we're going to talk about how to calculate the concentration of anything. So we'll see you then. Enjoy your day. Bye now.